Well, welcome. And here we are. We're going to start chapter 4 finally. And it's a kind of a short chapter, right? We didn't have a whole lot of reading and a pretty short prep guide. So our goal today is actually just this first little section here on chemical reactions. We're going to save stoichiometry and limiting react, all that, all the rest of it will happen on Wednesday and Friday. So just writing and balancing reactions today. Okay, well, okay, I lied. We're also to do some reviewing. So before we go forward, like you know what we always do, we always take one step back. And these are all on this slide, these are all definitions or concepts from, I want to say, our first day of class, but quite possibly sometime during our first week. These are all very early concepts. So what I want you to do is take just a minute and try and jot down or think about, if you're not jotting down, think about definitions of all these things or lists of them, or try and place when we did that. So I'll wait and give you a minute to do that thinking or writing.
Okay.
Oh, guys, you're fast. Yeah, that's a fast minute.
No, I meant okay, I'll do it.
Oh, okay. I was gonna say that was very fast. Awesome. Okay, I will wait now. I do have the chat box on, so if you have any questions that way, you can of course just yell them out, but you can also put them in the chat box as well. Hmm. So elements, yeah, things that can't be separated, right, or broken down physically or chemically, right? So it's both ways, right? We can't make them any simpler. And those are our 120 or so elements we have on our periodic table, right? So compounds, sort of, sort of similar, right? Our elements are one kind of our pure, right? So we had pure things and mixtures, right? So yeah, so a compound is, well, it's a group of atoms, but it's a little more than just a group, right? So they're not just hanging out together, they're actually bonded together, right? In that definite proportion. There's always, right? So that's our law of definite proportions from chapter 2, is that compounds are always made of the same atoms, always in the same proportions, right? So so no matter where we get it from, it's always got that same composition, right? So the same elements and the same proportions and same geometry, right? That was something that came up in our developmental practice 10 from over the weekend, right? That things could have the same chemical formula, but also have a different geometry, be put together differently. So yeah, so there's no physically separating them. So that's why I say it's more than just a group of atoms, right? We can't separate those atoms physically by sorting them out because they're bonded to each other. We would have to break those chemical bonds to turn them back into those atoms. All right. Yep. And an ion is definitely, it is something with a charge. So it could be an individual atom, or it could be a collection of atoms, right? Those polyatomic ions that I'll say know and love. Hopefully we know them now. Yes. Yes, a little thumbs up, hopefully. So yeah, that takes some time. So hopefully now that we've gotten over the exam, we can move forward and make sure that we've got those things memorized. So we're going to use that language. We're going to talk a lot about cations and anions. We're going to use that vocabulary. Next week, we're going to talk a little bit more about ions in parts of reactions and how they are in solutions. So those words are going to come back around again, and we're going to see that all semester, that we're going to use some words, we're going to learn about them, and then they might go away for a little bit, but then we come back to them. Okay, let's see what else we've got down there. States of matter. So I know that was definitely on our first day. States of matter. We talked about how many there were. So this is something we're going to start to see now. We're going to see that information, whether something is in the solid form, the liquid form, the gas form, or our brand new one, and in the aqueous form, dissolved in water. Yes. So we saw that little AQ that we wrote after some of our formulas for our acids, right? They have to be in water to do their acid-like behavior. So we're going to see those when we start writing our chemical reactions, right? So as we start to look at that, it makes a difference whether we're forming a solid, a liquid, a gas, or something that's dissolved in water. They're going to have different properties. They're going to have, right, different ways of collecting them, right? So that's going to be some information that we want to keep track of. For right now, in our work this week, I'm going to have to pretty much tell you what those states of matter are. There are, of course, some that you sort of know already, like oxygen is a gas, that sort of thing. But next week, starting next week, you'll learn some things, right? That you'll learn some concepts, some rules for how to decide if something is going to be a solid or if it's going to be dissolved in water. So that is coming up next week. So next week, chapter 5 has there's a lot of memorization in chapter 5. Good news, chapter 4 that we're in this week, none, zero things to memorize. So you can use this week to brush up on last week's memorization or look ahead to chapter 5 things to memorize, because chapter 5 does have a lot. And then I promise after that, not a whole lot more. Yeah. All right. How about chemical change? Now that's something that goes back to our first actual lab, right? We talked about it in our first week, but we looked at those. We actually saw them in our experiment when we finally got to be on campus and be in our lab.
Is it when matter changes, like, I wouldn't say like it doesn't freeze or anything, it just changes into something new. It can change
Changes
into
into
something
something
new.
new. Yeah. Yep. Our word for that is it changes its composition, right? So we've made a new material, right? So our little building blocks, our atoms have rearranged themselves into something new. So it's some process that changes what that material is made of, right? And conservation of mass, that's going to be a big one for us today. That goes back to chapter 2, so it's not really quite from our first week, but so in our chemical reactions, mass is not created or destroyed, right? So that was one of our foundational laws that helped us come up with atomic theory. That one is going to be sort of primary in when we start balancing reactions. But a chemical change is really that's a chemical reaction. So we will use those two words, chemical reaction, chemical change, or even chemical equation to represent sort of our symbols or our ways of describing that reaction. Those are all going to mean essentially the same thing. All right. That's our review. All right. So how do we know if a chemical reaction has taken place? What are some things you were looking for, say, when we did our first lab that gave you a hint that something had happened chemically? Yeah, bubbles and smoke is always good. We always look for something kind of dramatic, but those are still all telling you the same thing. There's something new there, right? That wasn't there before. right? Bubbles and smoke often go along with like energy being released. So that's another good one there. Right. So you're really looking for evidence, right? All of these things that are seeing are as evidence are ways of saying, hey, there's something there that wasn't there before. Right. So it could be, right, that the color changed, right? So now there's some new compound there that is purple when before it was blue, right? So that means that something new had to be made, right? Because the purple thing is now looking like a blue thing. So that's one way, forming a solid, right? I think we saw a couple of these. I think the very first one we did, right, where that solution gets kind of cloudy like that yellow solution forming here, right? Whenever it gets cloudy, that means there's some solid particles in there that are reflecting the light, so we can't see right through that test tube anymore. So forming a solid when we just mix together two liquids, that's another sign that something new is there that wasn't there before. Right? And of course, bubbles, right? If we mix vinegar and baking soda, that's one of our favorite little bubble reactions. And again, those bubbles weren't there before, right? We mixed a solid and a liquid and we end up with more bubbles. So that's kind of unusual. Of course, heat, right? Energy, either releasing heat or absorbing heat. So it might be getting very cold as well. That's another possibility as a sign of a chemical reaction, or like our poor little gummy bear, right? Another way energy could be released is in the form of light. So there's our poor gummy bear. Oh, he's pretty dramatic. Um, giving off that energy, right? Releasing that energy that was in the chemical bonds that way. So these are all evidence, right? Ways we can identify if something new was made, right? But it's not always this dramatic, right? Sometimes we're going to mix things together and it's going to look like absolutely nothing happened. Um, but that's just to our eyes, right? If we were able to shrink ourselves down to the molecular level, we might see that, hey, something new actually is forming, right? So maybe it's something that's invisible to our eyes. A good example is some reactions that happen in water. Lots of things that are dissolved in water are clear. So even when they react and form something new in the water, we might not see it with our eyes. Or some reactions are actually just very slow. So it doesn't look like things are changing when in fact they are, right? So things that are rusting, that's our iron turning into iron oxide by reacting with the oxygen in the air. That reaction is just really slow. So we can't, we don't, we look and we think, well, nothing's happening. When in fact a reaction is happening, it's just not happening on our time scale. So these reactions that you're seeing down here as evidence are all happening very quickly. And in fact, pretty much all of the reactions that we're going to see in our labs or in our demonstrations in class are all ones that happen pretty quickly because, again, right, we don't want to wait 3, 4, 7 years for a reaction to happen during our lab time, right? Our lab's already long enough. We don't need that. So don't be fooled that everything happens super fast. That's just an artifact of our class time, right? Making sure our reactions happen sometime today. All right, so we've got a chemical reaction. We know how we can recognize it. We've actually practiced it. We just didn't call it that. Um, so now we need to, we can kind of look at a specific reaction and we can describe it in words, right? We can tell the story of what happens during a reaction. So in this one, we could say solid sodium hydroxide reacts with aqueous, that means dissolved in water, aqueous sulfuric acid to produce aqueous sodium sulfate and water. In fact, this is one of those reactions that looks like nothing happened. Right? It's a clear liquid and we add a solid to it and we end up with a clear liquid. It doesn't look like really anything's happened in there. But we can translate, right, using our skills from chapter 3, how to go from a word or from the name of a compound to the symbols. And we can write that story that's up there in our shorthand, in our chemist's little shorthand using chemical symbols. And then in parentheses, we'll put the information about the phase, right? So is it a solid? Is it a liquid? What is it? So that would look like, right? So, and we should all be able to do this, right? Um, it would look like NaOH and then solid plus H2SO4, aqueous, forms or makes, produces, right? All those words, those are all what that arrow is. Na2SO4, aqueous plus H2O, liquid. So our ones in green are always on the left, right? So we always go from left to right. Our reactants, right? So again, not creatively named. They are the things we are putting together that are going to react. So those materials on the left side are going to be called our reactants, right? And then we've got an arrow, right? And that means produces or forms or creates or, you know, some word that indicates that that process is going forward. There's a change that's happening. It's actually kind of like the arrow in our dimensional analysis plans, right? Where we were changing, say, from grams into milligrams, right? That arrow was indicating that transformation process. That's what our arrow was indicating here, except instead of just transforming units like we were in dimensional analysis, we're actually transforming those materials into new materials. And then on the right, where we're going to put our products. So those are the things that are, I know, oddly enough, produced. These are the things that got made. These are the rearranged versions of those same atoms that we started with on the left side. So those were kind of our new words there, right? So we have reactants and we have products. What I do want to remind you is there's not always two of each. Sometimes there's just one as the reactant or just one as the product, or maybe there's 3 and 4. Like there could be any number. So it doesn't always have to be 2 and 2. This example happens to be 2 and 2. We'll see lots of examples that are not like that. But that's not what we're going to worry about when we balance anyways. It's not the number of molecules. It's always going to be about the number of atoms, right? Because we have to keep with conservation of mass. We can't have an atom appearing and disappearing. Can you see that our reaction here is not balanced? We've got some things that are appearing and disappearing pretty wildly, right? So if we look at even just our sodium, right? We've got 1 sodium on the reactant side and 2 on the product side. So this chemical reaction, this chemical equation isn't quite telling the whole story or the true story. It's definitely describing what we mixed together and what we formed, but it's not telling us the how manys. It's not getting the proportion right. So that's going to be a piece of what we want to do today. All right. So this previous one was unbalanced, right? We want to talk about, well, what does it mean to be balanced, right? So these are all the things that we're going to try and meet when we write our little shorthand stories. So it has to be consistent with the experiment, right? We can't include or have things going on in there that didn't actually happen, right? So we're not magically going to have copper sort of suddenly appear out of nowhere. It has to match the things we mix together as reactants and the new products that those reactants form. So our formulas have to be correct. We really have to be good at that. If we write the formulas incorrectly, those materials might not balance, and those materials might not be the ones that we originally mixed together. So formulas being correct is kind of a big deal. Our diatomic elements. All right, let's see if we can remember. See if we can write down I'll tell you there's 7 of them. Our 7 elements that come in 2s. They always come in pairs when they're elements, not when they're in compounds necessarily, when they're in elements. See if we can write those down. We'll see how much we remember from chapter 3. Gosh, it's only been like a few minutes and we've already touched on all of our chapters. Okay, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, right? We're missing one. We're missing the problem child, and the problem child is hydrogen. He's the smallest one, and he's always trouble. So, so hydrogen is our other one. All right. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. So when we use them in, so 6 of them are together on the periodic table. That hydrogen's, he's wandering all over the place. He's never where he belongs. So we have to keep our eye on that little one. So again, this is when we're going to start to use those diatomics when we say things react with oxygen or forms hydrogen or forms nitrogen. We're going to mean in their element form, which means we're going to have to show their formulas that they come in twos. So earlier in chapter 3, we were talking about those elements as part of a compound, and they weren't necessarily in twos when they're in compounds. So we're going to have to, right, pay careful attention to what's going on there. And also, we're only going to write down the materials that are involved in the reaction. So maybe if there was something else that happened to be in that container but didn't participate in that reaction, right, or the container itself, we're not including those in the chemical reaction. We're just focused on what's changing, right? What materials are changing. All right. So that's things that are consistent with the experiment. The second bullet point is it has to be consistent with the law of conservation of mass, right? We know that's true, right? We've measured a whole bunch of things and it seems to be always true. So here's how we're going to accomplish that. That means we have to have the same number of each kind of atom on each side of the arrow, right? So, and again, this is just kind of atoms. So they might not be in element form. They might be bound up in a compound on both sides, but the number of atoms on this side and the number of atoms on the other side have to be in balance. We have to account for all of our atoms. We can't have them poof, appear, and we can't have them poof, disappear, right? That we've got to account for all of them. And as a side note, right underneath it, it also has to have the same charge, right? We can't have electrons appearing and disappearing either. Most of our reactions, they're going to be neutral on both sides. We're going to have neutral, maybe compounds or elements on both sides. But we could have reactions with ions in them. And again, as long as we have the same charge, total charge on both sides, that's fine. We can have a negative charge on the reactant side as long as we have the same negative charge total on the product side. 99% of our reactions are going to be neutral on both sides. If you're doing biology or maybe remembering biology, some of those reactions have charges, net charges, but they're the same on both sides. If you wrote any reactions for biological processes, a lot of them involve things that are ions, right? Which is why our electrolytes in our bodies are so important to keep in balance, right? And to replace, right? As we sweat and lose some of them. All right, so that is our second thing. So consistent with experimental facts, consistent with the law of conservation of mass, and the exciting part is the last part. Well, it's the exciting part for me anyways. That is that our balanced chemical reaction is going to give us quantitative relationships. It's going to tell us how many. It's going to give us that how many information. How many of these does it take to react with how many of those in order to make a certain amount of something else, right? That's the exciting part, right? It's giving us that predictive how many information. So it's telling us the quantitative relationships, the mathematical proportions among our reactants and our products, right? So that is kind of a big deal, right? We see our little man there lifting weights. That's kind of a big deal. Spoiler alert, it's a conversion factor. As is everything, right? Every time we turn around, it's a conversion factor. We are not going to deal with that today. That is, again, that's for Wednesday. We'll save that sort of putting together what we do today with balancing reactions. We're going to put that together with our dimensional analysis and all those things we learned about in previous chapters, sort of quantitatively. We're going to do that on Wednesday and Friday. So we'll save that sort of last bullet point. We'll go into way more detail with that one on Wednesday. All right. Any questions so far? Okay, perfect. All righty. Well then, let's get to it, right? So how are we going to balance a chemical equation? Right? What is the plan here? Oh, yes. Little musical interlude. Ah, okay. Yeah. He'll go on for a little bit. Oh, it's going to be real hard to balance an equation from here on out without hearing that in the back of your head. So I'm sorry for that. All right, but this is how we do it. We are going to take our unbalanced equation and we're going to make it balanced by adding coefficients to this equation. We're going to add that information for the how many's, right? And we're going to do that. We're going to do that in an intentional way to try and make us have the same number of each atom on both sides of our chemical equation, on each side of our arrow. Okay. So these coefficients are going to be whole numbers, right? We do not want to see the F word, fractions, anywhere in our balanced equation, right? They don't make sense, right? Because we can't have a half a molecule, right? If we cut a molecule in half, we don't have that material anymore. That's that. So having a fraction as a coefficient doesn't make sense, right? We can't have a how many be not a whole number. So we have to be, they'll be whole numbers. We're going to put them in front of or to the left of whatever that substance's formula is. So whether it's an ion or an element or a compound, we're going to put that big number right out in front, right? So again, this is where it's so important, right, that we're paying attention when we handwrite it or when we're typing, right? We get that formatting right. That coefficient is going to be a big number out front, right? Our chemical symbols, right, are going to have a capital letter and maybe a small letter. And then there's going to be subscripts that go down that tell you how many of each atom in the compound. And then there's a charge. If there's a charge, that goes up and to the right. Right? So knowing where to put your eyes to see all that different information is going to be, again, an important skill. So that's why I've been kind of harping on that so much for the first few weeks, is just so we can get the geography, right, or the placement of all of that information just right. Because if we put that same information in different places, it means different things. All right. So we're going to put that number out in front, and it's only going to change the how many's. It's only going to change whether I have 1 or 2 or 5 of that whole ion or element or compound. But it's not changing the formula of it. It's not changing the composition. So the identity of that substance is staying the same, right? And it has to, right? If we're telling the story of that reaction, you can't be changing, right, what the formula is, because that's telling a different story. And we want to be able to tell the correct or the true story and also get this proportions right. Okay, all right. So in your packet of handouts from the stuff for chapters 3 and 4, this was one of the handouts. It has a little scale on one side, and on the other side, it had some practice chemical reactions, some descriptions of them that you can practice with. And it says that they're rules, and I'm just going to tell you the only one that's actually a rule is the first one, is that you cannot change the subscripts in order to balance your equation. You will be tempted to do that, right? If you run into trouble. But numbers 2 through 6 are just good ideas or guidelines from experience. You can call them pro tips if you want. Um, these are things that usually help, right? Or strategies to approach reactions with. We're going to do a bunch to practice with, and we'll see how each of them can be used. What situations might we use them in? Um, and the one at the bottom is the one I want to call to your attention right now, is that sometimes we just get stuck. We get stuck and we just can't seem to break free and balance that equation. It seems like you fix one thing and another thing gets messed up, and you fix that and another thing gets messed up, and you just kind of get stuck in that back and forth. Um, that is the time we just erase it all and start over, right? Check that your formulas are correct, because again, if you've written your formulas incorrectly, you might not be able to balance, right? You might have written a different story that doesn't have an ending. So you want to verify that your formulas are correct. Sometimes it helps to just practice these at a whiteboard, just the standing up or the colors or I don't know what it is. Um, I think it has something to do with easily erasing, right? You're not married to whatever you wrote down there. It's just easier to change. It's a little more flexible. But there's definitely going to be some trial and error components to this, especially at the beginning, if you haven't had a lot of experience with it. Okay, let's just let's just pick one. Let's just do one. This is the one that we described in words. This is our sodium hydroxide and sulfuric acid. So again, right? You can start wherever you want. Um, I always say, don't start with something. Don't start with an element that is in every single compound. You're not going to know where to put the coefficient to balance it. So that means typically things like oxygen, we're not going to start with oxygen. Oxygen's just a mess. Oxygen is in a lot of compounds. Not a good starting place. Our hydrogen is a little bit all over the place too. So let's not start with that one either. Um, our goal today is to kind of practice where to put our eyes, so we can quickly and efficiently move them around during our reaction, and balance it. So what the slides are going to do is every time we put in a coefficient, it's going to rewrite the whole equation. Please don't do that. That's unnecessary for you. You can just put the coefficients in and it'll be balanced. But on the slides, I wanted to make sure you could follow the steps, because right, once you've written in the first coefficient and then the second one, you don't know which order they happened in. So it's hard to figure out how we got from the beginning to where we are. So I'm gonna again just kind of rewrite each equation after we put in each coefficient. Wildly inefficient, but I hopefully instructive. Okay, so let's find something that's only in one material on each side. Um, Sodium, right? That's kind of an easy target there. It's right at the beginning, and it's only in one compound on the reactant side and only in one compound on the product side. So if we look at those, right, we look at how many sodiums are on the reactant side in our NaOH, how many are there? And then we'll compare that to how many sodiums are on the product side, right, in our Na2SO4. Okay. Hopefully, we can see that they are not balanced. We have sort of an extra sodium that just appeared out of nowhere. So we have to balance for that, right? And again, we can't just go over to our sodium hydroxide and put a little 2 next to the A in sodium, right? We can't add subscripts. That's changing the material. So we can't do that. But we can put a big number out front. And that's what those little blanks are right in front of them. A lot of the practice pages you'll see, are going to look just like that. There'll be a reaction and there'll just be blanks in front of everything so that you can fill them in with what coefficients it takes to balance them. All right. So to balance our sodium, we're going to have to put a great big 2 in front of sodium hydroxide. Right? So again, you can just put the 2 there, right? You don't have to rewrite the whole thing. I'm going to rewrite the whole thing here. So again, we can kind of follow along. So sodium, that was a good first choice. It was easy to see. It was only in one thing, and we've taken care of it. We still don't want to deal with oxygen or hydrogen right now. So what other element do we have that we can focus on? Yes, we have sulfur. It's easy to see, and it's only in one material on the reactant side and one material on the product side. All right, so we've got 1 sulfur on the reactant side and 1 sulfur on the product side. Great, they're balanced, right? We're done. We don't have to think about that anymore. That's the good news. The bad news is now we have to think about oxygen and hydrogen. So again, oxygen still a problem child. So let's deal with hydrogen. We'll just bite the bullet here and deal with hydrogen. So on the reactant side over here where NaOH is, right? Let's look at how many hydrogens there are, right? So remember that coefficient multiplies everything that follows it for that compound or ion or element. Right? So with this 2 out front and this 1 hydrogen here, we have 2 times 1 or 2 hydrogens over here in this material. But we have more hydrogens over here. We have more hydrogens in our sulfuric acid. We have 2 more hydrogens. So that's a total of 4 hydrogen atoms on the reactant side. Okay. Now we're going to head over to the product side. Right. So there's no hydrogens here in sodium sulfate, but we have 2 hydrogens in our water. Right. So remember, we have 4 on our reactant side and only 2 on our product side. Not balanced, right? So we have to think about, what can I multiply by 2 in order to make 4? Yeah, well, now we're doing algebra, right? Now we're doing a little bit of algebra. Yeah, so we're going to put that 2, right? We're going to need to put another coefficient in front of our water. And that is going to give us, again, you can just put it there. You don't have to rewrite the whole thing. But again, I'm going to rewrite it so you can kind of, again, follow the process. All right, so now we've got our hydrogens balanced. We did our sodiums, we did our sulfurs, right? When we put that 2 in front of water, we didn't mess up sodium or sulfur, so that's great. Well, now we need to deal with oxygen. But it is time. We've put it off long enough. So let's look. How many oxygens are in our NaOH? We've got a 2 out front and then 1 oxygen. So that's 2 times 1, or 2 oxygens. Right? In sulfuric acid, we have another 4 oxygens. So that is 6 altogether. Right? Use your calculator. No shame. No shame in using your calculator. So that's 6 oxygens on the reactant side. On the product side, we've got, again, 4 oxygens in our sulfate group, and then 2 times 1 oxygens in our water. So that's 4 plus 2 times 1. That also makes 6. So our oxygens, thank goodness, have all worked themselves out. That's pretty typical. Again, if we've written the formulas right, often the last, specifically oxygen, usually the last oxygen in all these ionic things tends to work itself out if we've written the formulas correctly. If it doesn't work out, that probably means we wrote the formulas incorrectly or forgot how to sort of count, maybe with parentheses or something like that. So yes, we can double check, and yes, they are correct, right? So we're done. You always know when you're done. You can always check that your reaction is balanced, right? That's the beautiful thing about these balancing reactions. Our goal, though, our goal, I don't think I said this earlier, our goal is to be able to write and balance a chemical reaction with 100% accuracy in less than a minute, right? We should not be spending 25 minutes balancing a reaction, okay? We spent probably 8 on this problem, but again, we're new at it today, so that's okay. We can spend a lot of time balancing today. But our goal is to work towards very quick balancing, very accurate balancing of our reactions, because we're going to do stuff with them. So we don't want to spend all day fussing with them. We want to be able to write them down properly and then use the information in them to do fun new chemistry things. All righty. So that's our goal. We're not going to be there today. So no panicking today. All right. Okay. So let's balance this one. If you have your little handout there, number 2, sort of guideline number 2 was that if you have polyatomic ions, and we have plenty in this reaction, they're kind of all over the place and they kind of looks like a mess and your head kind of hurts and you're like, I don't really want to balance this. That doesn't look fun. Oxygen's everywhere. Do not despair, right? If you can look at that reaction and see that your polyatomic ions didn't change, right? They're a polyatomic ion on one side and they're the same polyatomic ion on the other side. What you can effectively do is basically just, where there's parentheses, just make that a bubble, right? Put your polyatomic ions in a bubble, and let's treat them as one thing. Since they're not coming apart, right? And flinging out oxygens or nitrogen atoms in random directions and combining in different ways, if they're staying together as a polyatomic ion, we can balance them as one thing, right? So we'll see what that means. So here we can kind of put little bubbles around our nitrate groups, our NO3 groups. They stay together on both sides, and around our sulfate groups. They also stay together on both sides. All right. So again, same strategy as before, though. We're going to try and find something that is just in one element, an element that's just in one compound on each side, right? And one that's easy to see, right? Let's not make our eyes do extra work, right? We want to be quick about it. So we want to do things that our eyes can do easily, right? So I'm looking at aluminum, right? So we'll look at aluminum. Right? It's right at the beginning, right? It's at the front of the formula. So it's not like we have to go searching deep in a formula to find them. Right? So we look at aluminum. So on the reactant side, right, we've got 1 aluminum. And on the product side, we have 2. So what are we going to do to fix this? Or to balance it? Yeah, so we're going to put a 2 on the reactant side, specifically right in front of that aluminum, right? And that's going to balance out our aluminums, right? And while my eyes are right there, I just wrote that 2 down, and your eyes are right there. Let's look at the nitrate, because when you put that big 2 out front, that affects the nitrate as well. That 2 multiplies everything in that compound. So you just wrote that 2 down. So let's look right next to the aluminum, right? And ask ourselves, how many nitrates do we have now? Now that we put that big 2 out there, how many groups of nitrates do we have? So it's not 18. If you, this is a common thing, right? We're not looking at just the oxygens. We're looking at the whole group. So if you put a little circle around the nitrate, right? There's only 3 nitrates in that compound. And now there's a 2 out front. So you'll have 2 times 3 groups of nitrates, right? Because we don't want to deal with all those oxygens, right? We don't want to deal with individual oxygens. That's going to be a mess. They're in every single compound. We won't know where to put a coefficient. So we're going to treat that nitrate group as one group. In aluminum nitrate, there's 3 of the groups of nitrate. So yes, there will be 6 groups of nitrate all together, right? That 2 out front times the 3 nitrate groups, that's 6 nitrate groups, right? And now that we've established that, we can bring our eyes down to the other end of the on our product side and find the nitrate group and see how many there are. Right? So when we just take that information and we let our eyes slide to the end, right? All the way to the end where the nitrate group is in HNO3. And we ask ourselves, well, now how many nitrate groups are over here? Right? So on the product side, we've only got 1 nitrate group. So they're clearly not balanced. So what are we going to do to balance that? Yeah, we're going to put a 6 right in front of that nitrate. So you see how we're kind of moving our eyes and then writing. So our pen is following our eyes, right? And our eyes are moving efficiently. So yeah, we're going to put a 6 in front of that nitrate group, right? And again, remember that's where our eyes are. Our eyes are right here, right where we just wrote that 6. So let's look at the hydrogen. They're right next to it. So let's figure it out. When we put that 6 in front of HNO3, that changed the nitrate groups to have 6 of them, but it also changed our hydrogens, right? So how many hydrogens do we have now that we put that big 6 out front? Yeah, we have 6 times 1. Again, we don't write the 1 subscript. So we've got 6 hydrogens. So we just, right? And we're going to take that information and we're going to let our eyes slide backwards along that reaction until we find the hydrogens. This is the only place they are. They're in the H2SO4 from the beginning, right? Remember, we're trying to come up with 6 of them, right? And we've only got 2. So what do we need to put right in front of our H2SO4 to make this work? Yeah, we're gonna put a 3 there, right? And now our eyes are right there, right? And again, if we put that 3 in front of H2SO4, we've messed up the SO4s. So we'll look at how many groups of SO4, right? So not how many oxygens, right? How many, right? Draw a little circle around the SO4. How many of those groups are there? Right? So again, that little 4 at the end refers just to the oxygens in SO4, right? So take your pencil and draw a circle all the way around the SO4. Yeah, yeah. And that tells you you've got 3 times, right, 1 or 3 groups of SO4, right? And now we're going to look on the other side and see how many groups of SO4 do we have on the product side. It's like magic, right? Just like magic, we have 3 groups of SO4 on the product side. So the SO4s kind of work themselves out. And again, that should happen if we have just a bunch of ionic compounds just kind of moving around and changing partners, right? If we wrote those formulas right, we should be able to put a number here and a number there, and right, maybe a third number somewhere. But that last ion should work out if we've written our formulas correctly. If you're stuck in sort of a back and forth where you keep changing coefficients and messing up other ions, probably wrote the formula wrong. So that's step number 7 at that point if we start going back and forth too many times. Right? Or you read the formula wrong, right? Maybe you thought there were 4 groups of SO4 instead of 3, right? So that's one way to get yourself in trouble. Again, the more familiar you got with these polyatomic ions, that won't even happen, right? You won't make those errors. So yeah, so we don't have to do anything more, right? We can stop and sort of double check and count all of our atoms again. But they should all be balanced. Okay. Give us any questions so far? Are we ready to just keep practicing? Okay, we will keep practicing. All right. Combustion of butane. All right. I'm really sorry we're doing this online instead of in person because we actually did set stuff on fire today. But combustion, it's a common reaction. This is one of the reactions you're actually going to be able to predict the products of. As long as I tell you what it is, we are combusting or setting on fire. So C4H10 is butane. It's in butane lighters and those little things you use to light your candles with. C4H10, that's its formula. When you set things on fire, what else do you need to have a fire? Besides the thing you're setting on fire, what else do you need? You need oxygen. Yeah. Right. A little spark and then oxygen. This is why you stop, drop, and roll if you catch yourself on fire. You are effectively hiding your material that's on fire, that'd be you, from the oxygen, right? And so if oxygen can't get to that material, then that reaction can't happen, right? And that's what stops the fire. It's that you've taken away one of the reactants so that that reaction can't happen if they're not both there. All right. So oxygen is going to be our other reactant here, right? And we have to remember, right? Oxygen comes in twos when he's in his element form, right? And hope we all know oxygen is a gas. So when you write that on your reactant side, right, oxygen should have a little parentheses and a little G after it, oxygen being a gas. All right. And what forms, right? What are some things that form when we burn things made of carbons and hydrogens, like, well, any of our fossil fuels, right? They all have a similar structure. They're all made of carbons and hydrogens. So when we burn them, right, if you're paying attention to environmental things, what is it that we're producing? We are making CO2, right, which is one of the challenges, right? That a lot of our fuels, a lot of our ways of getting energy out of these chemical compounds involves producing CO2. So that's one thing that's going to be formed. Anytime we burn things made of carbons, hydrogens, or oxygens, we're going to get CO2. And then our hydrogens are all going to end up in water form, right? So we're also making water, which is not the problem when we burn these things, but we are releasing water vapor, right? Because it's hot when we burn these things. That's why we burn them, to get the energy out of them, to release that heat energy. So our reaction is going to look like our starting material, right? And I will have to tell you whether it's a gas or a liquid or a solid. We don't necessarily know those things. But they're always going to look like, right? They're going to all react with oxygen. And then if the material we started with was made of carbons, hydrogens, oxygens, we're going to form carbon dioxide gas and water gas. So this is a reaction that you're actually going to be able to predict. If I tell you the starting material, you should be able to finish that whole reaction, right? We know oxygen's another reactant. I'm going to make carbon dioxide and water. So yeah, so we don't have to wait until next week to be able to predict reactions. This one we can predict right now. But our goal today is to practice balancing. So let's get on with balancing. The next rule, the next sort of guideline, I guess, is if there's an element in our reaction somewhere in its element form, we're looking at oxygen right now, balance that one last. Right? And the reason for that is that you can put a coefficient in front of oxygen, the O2, and it won't mess up all the other elements you've already balanced. So it makes sense to leave that element until the very last step. All right. So let's pick another element to look at. Right? Right? Carbon, right? That makes sense, right? It's right in the front, right? It's only in one material on both sides. So we can focus on carbon, right? And we can see how many carbons are on the reactant side, and we'll see how many are on the product side. Right? And then we'll think, well, they're not balanced. So what do I need to do to have the same number of carbons on both sides? Well, so we're going to put a 4. We're going to put a coefficient of 4 um, in front of our CO2, right? So we're not going to put a little 4 as a subscript for our carbon, right? That then it wouldn't be carbon dioxide anymore. We will have changed the story, right? So we're going to add coefficients, right, on those blank lines there. So hopefully having those blank lines there kind of reminds you that that's where you should be adding your numbers to. Don't be changing the formulas. All right, so that balances the carbon. So let's focus on the hydrogen now, right? So you've got to kind of train your eyes, right, to look just at the hydrogen part, right? Not get distracted by the whole reaction, right? We don't want to deal with that. We want to just focus on the hydrogen part. So there's 10 hydrogens on the reactant side, and then we'll slide our eyes down to the end, right? And there's our hydrogens in water form, and there's only 2 of them. All right, so it's always about multiplying. So what number do we need to put on this line in front of water so that when we multiply it by 2, we end up with 10 hydrogens? All right, yeah, so we're going to put a 5 right in front of that hydrogen in our water. Now that 5, right, applies to everything in the water molecule. So it's also going to multiply the oxygens. And we've avoided them long enough, so let's just deal with oxygen. All right, so we've got, for the CO2 part, we've got 4 times 2 oxygens. So that's 8 altogether, right? And maybe you just want to jot it down so you don't have to hold it in your brain, right? Just put a little, right? Just make a little note that you have 8 of them somewhere. It's small, so it doesn't look like they're accidentally coefficients in your balancing. And then you've got 5 times 1 oxygens over here in the water molecule. So that's another 5. So you've got 8 plus 5, which again, calculator, perfectly reasonable thing to do. That gives you 13 oxygens altogether. That's on the product side. On the reactant side, right? Let's go back to the reactant side. You've got 2 oxygens. All right. So what do you need to multiply by 2 in order to get 13? Yeah. So yeah, the answer is 6.5, right? That's a math problem. And the answer is I need to multiply by 6.5, but that makes us unhappy, doesn't it? Right? I promised you that we don't want the F word. We don't want fractions today. And that 6.5 totally looks like a fraction. We don't want that. So, but we don't have a choice, right? We can't balance an odd number of oxygens when they come in twos. We know we're going to need a fraction of an O2 molecule, but that doesn't make sense. So here's what we're going to do. We're going to handle this the same way we handled those weird fractions that showed up in our empirical formulas, right? When we got number of moles and some of them were whole numbers and some of them looked like they had decimal places in them. Our strategy was to multiply by something to get rid of the fractions, right? So we're going to write down 6.5 for just a split second. Do not be alarmed. All right, there it is. So it is technically balanced right now, but it doesn't make sense. It doesn't make sense. When we write our reactions, when we balance them, we want to use the smallest numbers possible, but we want them to be whole numbers because we can't have a half of a molecule. That just doesn't make sense. So our strategy when we had a fraction was to multiply by something, right? But we have to multiply everything by something because right now it's balanced, right? Right now everything's in the right proportion. It's just that we don't like that fraction there. So if we multiply by something, the smallest something we can get away with, to get rid of that fraction, everything will still be balanced, but we won't have that disgusting fraction anymore. So if our fraction is a half, right, 6.5. What should we multiply by to get rid of that? Yep, we are going to multiply by 2, right? That's how we get rid of a fraction of a half, right? So we did that with our empirical formula work, right? it's the same process. This is kind of like the empirical formula for the reaction, right? We're writing the smallest whole number proportions for these compounds and elements, how they combine, right? So we want to use the smallest numbers possible. So we don't want to, have numbers like 400 and 500, but we want the simplest whole numbers, right? And since we've got that 6.5 looking at us, let's fix that. Let's multiply everything by 2. Every coefficient is going to get multiplied by 2. We're not changing the formulas, right? We're not multiplying the formulas by 2. We're multiplying the coefficients by 2. All right, and don't forget that first one, that first blank spot, that's a coefficient of 1. We just don't write down the ones because it's messy. Okay, you can write them in if you want. If it makes you feel better, you can put the ones in there. But when you read them, like in textbooks and in problems, that one isn't going to be explicitly written out. But it's not wrong if you want to include it, just so that you kind of are reminded of it. All right, so multiply by 2. Every coefficient gets 2 times bigger. Okay? Now we have all whole numbers, and all the atoms are balanced, right? Same number of atoms on each side. We have the right proportions, right? To keep conservation of mass still in play. We don't have any disgusting fractions. So yay. This will happen with our diatomic elements. That's our most common reason that this happens, because those elements come in twos. If we have an odd number of them involved in our reactants or products, it's going to happen, right? We're not going to be able to avoid it, unfortunately. So we're just going to have to kind of deal with it. But yeah, we're never going to leave the fraction there. So even if it's just there temporarily, we can make it go away. So this is one case where you might rewrite that reaction after you've balanced it and it's got a weird fraction that you might just want to rewrite it, getting rid of that fraction, doubling all the coefficients. If for some reason we had a fraction of 0.3, like a third of something, or a fourth or quarter of something, right? Then we multiply by 3 or 4 to get rid of it. But the 2, most common, we're going to see it a lot in our combustion reactions. That is the most common place it will be. But we have a strategy to take care of it. That's the good news. All right. Let's try another combustion, right? Now that we talked about what gross things can happen with the combustion, let's set some iron on fire, right? Burning or combusting steel wool. This is the rusting process. This is actually what happens when things rust. But it's a slow reaction. It's not very dramatic. So it doesn't look like you're burning or combusting it, but that's actually what is happening. So iron, right? When we set it on fire, right? We're going to be reacting it with oxygen. And what we form is rust. It's iron 3 oxide. That's what we get out of it. A ridiculously slow reaction, and so it's not looking very dramatic, but it does happen. So when we look at this reaction, right, our strategy we used last time was, if there's an element in its element form, sort of sitting there all by himself, we'll do that one last. So we look at this and we're like, well, they're both elements. We can't do them both last. Now what? Now where do I even get started? So let's take a look at the rule right underneath it, which was going to be, is that rule number 4? We have to rule number 4 now, I think. Which is that if there's an odd number of an element on one side and an even number on the other. So this is kind of the situation we just had. We had an odd number of oxygens and they came in twos, right? So the strategy that's outlined in that particular guideline is, you know what, let's just make the odd side even. Let's just avoid that whole problem of fractions right from the beginning, right as soon as I recognize, hey, there's an odd number on this side and an even number on the other. That's not going to work out. I don't like fractions. I'm going to make the odd side even. I'm just going to start with that. I'm just going to deal with that right away. So the odd side is the product side. There's an odd number of oxygens in Fe2O3. but there's an even number of oxygens in the O2 on the reactant side. And you're like, wow, this is not going to end well. I'm going to make the odd side even. And you're going, well, how do I do that? How do you make any number an even number? How do you guarantee that you have an even number? You multiply by 2. So let's just put a great big 2 right in front of Fe2O3. Let's just solve this problem before it even develops. Okay? You don't have to do this, right? But eventually we're going to come to the same end result. This way you just kind of avoid that awful feeling that you get when you see a fraction right at the beginning. Right? So we just put this 2 in front here, right? And that makes our oxygens, right? It's not a 3 anymore. It's 2 times 3. So we have 6 oxygens. And you're like, well, that feels better. That's an even number, right? Let's take that information. Let's scoot our eyes, slide it back towards the reactant side. How are we going to get 6 oxygens when they come in twos? What do I need to put in front of my O2 to balance out and have 6 oxygens? Yeah, so we're going to put a 3 there. See, that was way better than thinking about fractions, wasn't it? Right? You're like, ugh, other ways you got to think about a fraction and then you have to take care of it later on. We're like, let's just do it up front. We've got our oxygens taken care of. Right? And now there's only one other element to deal with, and that's our iron. So let's bring our eyes back over to our iron where we have that big 2 coefficient in front of our iron 3 oxide. Right? How many irons do we have all together on the product side? Yeah, we've got 4. So 2, the coefficient out front, times 2, the subscript. That makes 4 irons altogether. So what do we need to do to balance out our irons? Our iron. That's hard to say. Our irons. Yeah, we're going to put a 4 right in front of our single iron. And we can do that, right? Because it's an element. As soon as we put that in there, we haven't messed up everything else. So we can just move along, right? And be done with that particular balancing. All right. We did have a little intermission here. The rest, we just got more things to practice with. So do you need an intermission? Okay. All righty. Well, think about how well you're doing so far, right? What's come easy to you? What are the challenges, right? Is it reading the formulas? Is it knowing what coefficient to put there? Is it just getting started, right? So those are all different things we can work on if you have individual needs. Just a little place to think about it. So we'll go through, I don't know, like 6 more, I think, here. So here's a skill, right? Write and balance this chemical reaction. I'm going to give it to you in words, right? I've described everything so you know what phases to use. You have enough knowledge now to be able to do this question, to write and balance this chemical reaction. So the goal was to be able to do this in a minute or less with 100% accuracy. That's not going to happen today. If that does happen today, that's great. That's exciting. So I'm going to try and be quiet for a little bit and let you let you have a minute or two, let's say 2 because we're new at this, to try and fully write out that reaction in with all its chemical symbols, with all the phase information in place and balance it. Okay, so your clock is started now. Well, that was less than 2 minutes. Awesome. Let's see how we're doing. Right. So check first that you got the right formulas, right? Because it doesn't matter if you balance if we've got the wrong formulas, right? We're not going to have the right information or proportions, right? The big one on this one was remembering our little friend hydrogen way at the end there comes in twos, right? Which might make it a challenge, right? So we're going to balance for him last. Yes, if you don't have that there, yeah, if you don't have him in twos, you'll have it'll you might still have balanced it, right? But you're not going to have the right formulas. All right. So magnesium is just one of those elements that comes by itself, and we said it was solid, right? It's a metal, right? So we can probably you could have figured that out on your own that it was a solid. Hydrochloric acid, right? So again, if it's an acid, right, it's got to be aqueous, right? So HCl. And then magnesium chloride, I think we've done that one a couple times in class. But it was aqueous, so you had to put that little AQ at the end. And then hydrogen gas. So you might have known that hydrogen was a gas. It's non-metal and it's very lightweight. We use it in balloons and so those airships. But yes, it does come in. It does come in tubes. All right, so it's one of our 7 diatomics. All right. But once you've got that right, then the balancing, again, this one's not too bad to balance. It's just a few numbers here or there, right? So the magnesium's already balanced, right? So if we just move our eyes around there, right? Our magnesium is already balanced. Our hydrogen is not balanced, but we can balance that with a 2 in front of our HCl. And that 2 in front of HCl also applies to the chlorine. So there's 2 chlorines, and we're like, great, there's 2 chlorines over here on our product side. So everything is balanced with just the 2 in there. Okay. All right. So again, you kind of start to see if we haven't got the formulas right, that's going to change those coefficients, right? We're not going to be telling the same story or the correct story. Let's try another one. All right. So write and balance this chemical reaction. So there's plenty of problems just like this in both the practice on Blackboard or in the Science Learning Center. And on your developmental practice. 11, I think is what we're up to 11. There's some where you just balance it where you already know the formula. And then there's some where you have to actually kind of put 2 skills together, the writing and the balancing. So again, this one, let's give yourself a minute and a half. We'll see how close we can get to a minute today with writing it and balancing it. That takes a little more work, especially with the polyatomic ions and the not well-behaved ions with the Roman numbers in their name. That's always a little extra work that it takes. All righty, let's take a look at it. In about a minute and a half. All right, so first thing to do is to check, did we get all the formulas correct? Right, so that's our very first step. That's an old step from before. And again, so if we haven't gotten that right, then the balancing may or may not work out. Again, right now, I have to tell you whether something's aqueous or solid or what its phase is in. But next week, by the end of the week, you're going to be able to both predict what the products are and decide if they're solid or aqueous in these situations. So again, for right now, for this week, I have to tell you that information. But very, very soon you'll be able to, just knowing what we start with, knowing what the two things are we mix together, you'll be able to predict the formulas of the products and the phases of the products. So if you check out some balancing practice from the Science Learning Center, it may have some of those where you have to do the predicting. So save those for next week. We're not quite there yet, but any of the ones where it's just balancing, where you've got everything all laid out for you and there's just blanks for you to fill in for coefficients, that's the kind of practice you want right now. There are some practices just for combustion, and those ones you can predict what the products are right now. So those are again the more challenging ones. So start with these more basic ones. And our Blackboard also has some additional ones. They're different. And they're different from the ones that are going to be in your developmental practice. So again, hopefully lots to practice with. Okay, so our lead was already balanced, right? So our nitrates, there's 2 nitrate groups. So we put a 2 over here, right? Which messed up our potassium, right? So our potassium has 2. So now we're going to bounce our I's back and put a 2 in front of the potassium iodide, right? And that changed our iodide count from 1 originally to now 2 times 1. So 2 iodines, you're like, great, oh, that all worked out. Right? So that is the correct balanced one, right? So again, we're just we're not necessarily going from left to right. We're moving through that reaction in sort of an efficient way, sort of dealing with the effects, say, of that coefficient. When we use it to fix one part of the molecule, hey, well, that changed the other part. So now let's look at that part of the molecule and figure out how that works, rather than kind of getting lost or losing track of that. That lets you kind of only keep one thing in your mind at a time. As soon as we try and hold multiple things in our brain, that's when we lose track of things. So make sure, again, that you're just sort of trying to be efficient, right? You can use your fingers. Those are okay for marking where you are. That kind of helps your eyes to focus on the important thing and not get distracted by the whole rest of the reaction. All right, so here's another one for you. Solid sodium reacts with water. Right? So water is our word for liquid H2O. Again, we're assuming, right? And hopefully by now, everyone's figured out that water is H2O. And water is, again, the word we use for it in its liquid form. Ice would be what we would call it if it were in its solid form, or water vapor or steam would be what we call it when it's in its gas form. So whenever we see water, know that it means liquid. Okay, to form, right? So that's right. Those are our words for the arrow. To form aqueous sodium hydroxide and hydrogen gas. All right, so let's see how we do with this one. I'll put the timer on here. We'll reconvene in 2 minutes tops, or whenever we've decided we've got it worked out. Alrighty. Let's take a look at this one. Again, this one has its own little challenges. All right, so let's make sure we've got the formulas right. So sodium, again, it's an element that comes just as in ones, right? We talked liquid water to death there, H2O liquid. Sodium hydroxide, we've done that one a bunch of times. Yeah, and our good friend hydrogen again, right? So yeah, we were not fooled by it more than once. So we're getting some good practice in with those diatomics. All right, so is it balanced? Is this reaction balanced as it is written? It is not. It almost looks like it is. It's very close to being balanced. So there are several strategies you can use with this one to balance it. One thing you can do is recognize that we have sort of that same situation brewing again, where we have an odd number of hydrogens on one side and an even number on the other side. So on the product side, we have an odd number of hydrogens. There's 3 hydrogens. And on the reactant side, we've got an even number, right? This time, because hydrogen comes in twos as in the form of water. So we can use that strategy of making the odd side even. That's one strategy. We could also put in fractions and then get rid of them later on. So again, there's not a right way or a wrong way. There's what makes sense for you, right? What path are you seeing more easily? So I made the odd side even because I really dislike fractions apparently. So I took my compound with the odd number of hydrogens, NaOH, and I put a 2 in front of it just to stop that nonsense completely. Um, and of course, when I do that, right now I've got to deal with my oxygens, right, and make sure they're all taken care of, or deal with my hydrogens, make sure they're all taken care of, and then finally deal with the sodiums. Right, we're going to do that one last, right, because sodium's an element all by himself, right? Hydrogen's an element, and he's all by himself, but he's also bound up in these other compounds. So we're not going to do hydrogen last. We're going to do sodium last. All right. So to balance the hydrogens, we're going to need a 2 in front of the water, right? And to balance our sodiums, we're also going to need a 2 in front of our sodium. And that takes care of it. So we put 2's everywhere except for in front of our little diatomic. Yeah. So again, no one right way to do it, right? Whichever path you take, we should get to the same, we're going to get to the same ending. So again, very much like dimensional analysis, there's more than one way to get from, right, the starting point to the ending point, right? What way is the best is the way that makes sense to you, right? That you can do efficiently and correctly. And we ended up with, right, the smallest whole numbers we could possibly end up with here. Right. Okay, let's just go right to the balancing here. So this is another one where it almost looks balanced, or it's hard to see if it's balanced because there's just a lot of elements that all look the same after a while. Just a lot of H's and O's and 2's and yeah. So being able to sort of focus your attention on the symbol, right? So being comfortable and recognizing those symbols and sort of being able to internally know that the H is hydrogen and the O is oxygen, right? Thinking of them as more than just sort of scratches on the paper, and know what that 2 means, whether it's at the bottom or at the top or in front of. So that's going to take, like I said, just a little bit of experience and exposure to this. So the more you can practice with these, right, the better you're going to get at sort of knowing how to move your eyes around those reactions. Is it balanced? So it's not balanced. Again, it's trying to be balanced. So you can use the same strategy as last time, right? This is another one of those ones where we've got an odd number of an element on one side and an even on the other. You may see a different way to approach it that makes sense to you. So let's give you well 30 seconds because I've been yakking quite a bit. So you probably already got halfway through it. Okay. All right. Hopefully you're starting to like get to the end and recognize like, oh, I'm done. It's balanced, right? You feel starting to feel that confidence that like, hey, I'm pretty sure of this. Yeah. So for here, right, again, we made the odd side even, right? And then finally took care of our oxygens and that was it. Yep. So we've got a 2 and then a 2 on the product side and a, right, again, it's blank in front of the oxygen. That just means there's a 1 there. So again, you can write it in or not, but again, practical reasons or sort of technical, you would just leave it blank, right? So the same reason we leave it blank, we don't write H2O1 for water. Right? We just leave that as water. Okay. All right. I think these might be our last ones here. It's our poor little gummy bear again. Um, it was actually 2 reactions that happened when we blasted our gummy bear away. So here he is. Here he is being blasted away again. All right. So let's try and balance those 2. Try and do this without, I'm going to try and do these and show you without putting in a new line after each one. Right. So try and do that. If you've been writing them out after each step, try and do it in this shorter way where you just put the numbers in. Right? Just move around that reaction until you're happy that it's all balanced. Yeah. So that first one is a little more straightforward, a little more familiar. Those combustion reactions, that second one, those are always more challenging. And this one's extra challenging because it has oxygens in the original compound that we set on fire. So yeah, so that was the sugar. That's sucrose, that original, that is our gummy bear. This is mostly sugar combining with oxygen to form carbon dioxide and water vapor. So it's a little harder to like, well, how do I deal with that oxygen being already over there? The numbers are usually bigger with combustion reactions. So that's already like a little more of a challenge when you're not just dealing with 1s and 2s and 3s, but you're dealing with 11s and 6s and 9s. Those are always a little more challenging. All right. So again, at the beginning, right, those combustion reactions are always going to take longer, right? But, right, with a little bit of practice, right, maybe you can finish them in a minute and not, the idea is though we don't want to take 20 minutes to balance, right? That's our goal. So, right, taking a little longer on those combustions makes sense because they are usually a little more complicated. All right, here's the results. Okay. So this time again, we didn't have to write the reaction, right? That was already given to us. We just had to fill in the blanks. All right, how did we do out there? So the first one was a case where we had, again, an odd number and an even number, so you could approach it that way. Let's look at the second one a little more closely, right? We can do that. Let me stop sharing this screen and we'll go to my little paper here so we can kind of act that one out and see where that came from. Let's take a look at. It would help if I plugged my camera in. That would be better. Let's look at that. All right, so there's our reaction. Right, so we'll start with our carbons. Right, so there's 12 carbons over here. Right, and there's only one over here. Right, so to balance that, we're going to have to put a 12 right, in front of our carbon. Yeah, right, it's a bigger molecule. So yeah, we're going to be making more carbon dioxide. All right, with our hydrogens, we've got 22 on the reactant side and only 2 on the product side. So what coefficient do we want to put here in front of our hydrogen? Or in front of our water? That's not just the hydrogen, but the hydrogen in water.
11.
11. Yep, that is our. Right, so it's something that we're going to multiply by 2 in order to get 22. And you're like, well, great. That was kind of the easy part, right? The carbon and the hydrogen are kind of nice and well behaved. The oxygen is a great big disastrous mess. So let's deal with him. All right. So how many oxygens are right here in the carbon dioxide part? Okay, so it's going to be 12 times 2.
24.
Yeah, like I gotta get my calculator out. Anything bigger than 9, my calculator's coming out. It just is. All right, so that's 24 from there. So and then over here with water, we've got 11 times 1, right? Or another 11. And we put those together, right? I think we get 35.
Yeah, that's what I got the first time too.
Okay. And then you've got okay, so that's all on the product side. So we do have to get our act together and say, well, if there's 35 oxygen atoms on the product side, then all together over here on the reactant side, there also better be 35. That's going to be our goal. Right? Here's the thing though, 11 of these are already over here, right? So we can't ignore the fact that some are already over here. So we can't get all 35 oxygens out of our O2. Right? Because that would be ignoring the 11 that we started with to begin with. So if we've started with 11 from over here, right? How many more do we need from this guy? Right? So we need 35 total. 11 of them are already accounted for over here, right? And we don't want to put coefficients over here, right? That would be disastrous. If we put
So
coefficients,
24.
yeah, that would mess up everything, wouldn't it? Yeah, so we're going to need 24 from this guy, right? So what are we going to put in front of it? So in front of our O2, so that when we multiply it by 2, we're going to get 24.
12.
We're going to get a 12 right here. Yeah. Yeah. So sometimes we forget about the oxygen that's already in our beginning material. So lucky
Yeah, that's
us.
what I did.
Yeah, and that happens, right? Because we haven't done an example like that. So now that we have, it's not going to fool you next time. We did get lucky, right? And we didn't have fractions. We didn't end up with a fraction, because if we ended up with a fraction, then we would have to multiply everything by 2 and take care of it. But for this one, yeah, so it was just tricky in that we had some oxygens hiding in our beginning material there. Okay,
Okay.
back to where we were. All right, and I want to say that in fact is where we're going to end today, right? So we will pick up on Wednesday with putting this together with our dimensional analysis stuff from the whole rest of the semester. So I'm going to say not a lot of new stuff, right? There'll be a couple of new words that we throw out there. And again, integrating is always the challenging part. But right, not a lot of new, but definitely more. We're going to look at the math part of this, which we haven't looked at yet in this chapter. Alrighty, so let me end our recording here.